Hey Janelle, I am going to try my best to get through 4 problems that I think are going to help you with the homework. I have 6.5 minutes to do it because that's how much memory I have left on my camera. So here we go. The first thing that I want to walk you through is drawing a free body diagram for an object that experiences a net force. So we have a block that's on a surface, so we know immediately, and this block I'm just saying is 5 kilograms. So we know that we have a force of gravity pulling down, and the force of gravity can always be found by mass times the acceleration due to gravity, which we use the symbol g, but we've been using it in this class over and over again. It's just 10 meters per second squared. So our mass is 5, the 10 meters per second squared, 5 times 10, we get 50, and that's 50 newtons pulling down. It's also balanced by a normal force. Now this thing isn't moving up or down in the y direction, so the normal force must balance out with the force of gravity. So we have 50 newtons up. Now this thing would just be staying in position if those were the only 2 forces. But let's suppose that I come along and I push this thing with, I don't know, 100 newtons. So if I push this with 100 newtons, now that's the net force, because these two cancel out, 50 and 50, in the y direction. So I push with 100 newtons, and we're supposing that the surface is frictionless. So we would use Newton's beautiful second law equation, F net equals ma. Our net force is 100 newtons. The mass of the object is 5 kilograms, and we could solve for the acceleration. Fairly simple. 100 divided by 5, and we can solve for acceleration in meters per second squared. Okay, so what if there is friction? So what if I push with 100 newtons, and we of course still have our force of gravity? It's still the same because this block is still the same. I'm still calling this 5 kilograms. We would still have 50 newtons. And then I still have the normal force, Fn, of 50 newtons because they balance out. Now, I push with 100 newtons, but I also experience some friction of 20 newtons. So the net force is going to be 80 newtons, and that's going to go to the right. So once again, I can use Newton's second law, and I can say, well, the net force is going to be 80 newtons. My mass is going to be still 5 kilograms, and I can figure out my acceleration. So simple enough, and that's what the first 4 problems are doing. You're either solving for the acceleration, you might be solving for the force of friction. Let me check. No, it gives you the force of friction. But there is a problem where it says that the block is moving at a constant velocity. Now, if the block is moving at a constant velocity, it means that all the forces are balanced. So this 100 newtons right here would be balanced with the force of friction of 100 newtons. So these two would balance out, so the block could move at a constant velocity. So keep an eye out for that. There's also a couple incline problems. So I'm going to do one incline problem without friction, then I'll move to an example with friction. Now, if I have an incline, no friction, I still have my force of gravity pulling down. This thing pulls the block straight down like that. And still, no variation. My force of gravity is still just the mass, which is 5, times 10 meters per second squared, so I get 50 newtons. And I have my normal force, but this time, because I'm at an incline, my normal force is always going to be perpendicular to the surface. So that's how I draw it. Now, this is where it gets funky. I actually have to twist my coordinate system. So in these problems, I was doing my coordinate system as x direction is horizontal, y direction is vertical. So y, x. Now I have to shift it up. And I'm going to shift my x and y like so. So that my x is parallel with my incline, my y is perpendicular. And now I have to use some trig. So bear with me. I have to break up this vector here into a y component and an x component. See that right triangle there? So that's going to be my x component of gravity. This is going to be my y component of gravity. And this angle right there is going to be 20. It's always going to be the same as whatever the incline is. I have a minute and a half left on this video. I'm going to try and get this as fast as possible. But you know this hypotenuse is 50 newtons. You know the angle here. So you can solve for the force of gravity in the x direction. You can solve for the force of gravity in the y direction. And you know that the force of gravity in the y direction is going to balance out with the force, or the normal force, because this block isn't accelerating in the y direction. It's just going to move down the slope. It's just going to move in the x direction. So whatever I solve for in the force of gravity in the y, it's going to equal my normal force. And then I can solve for the force of gravity in my x. So how do I do that? Well, I use this triangle. I'm just going to blow it up over here. So this is 50. This is 20 degrees. So I could do, well, this side is opposite. So if I do SOHCAHTOA, I'm going to need to do sine of 20 equals opposite O over 50. So 50 times sine of 20 will give me the opposite, and that will be the force that pulls this block down the surface. And I can do F equals ma with that.